The sine function enables you to calculate distances when you're not able to make an accurate measurement. To this day, it's used in architecture and engineering. The Indians used it to survey the land around them, navigate the seas, and ultimately chart the depths of space itself. It was central to the work of observatories like this one in Delhi, where astronomers would study the stars.
The Indian astronomers could use trigonometry to work out the relative distance between the Earth and the Moon and the Earth and the Sun. You can only make the calculation when the Moon is half full, because that's when it's directly opposite the Sun. So the Sun, Moon and Earth create a right-angled triangle.
Now the Indians could measure that the angle between the Sun and the observatory was 1/7 of a degree. The sine function of 1/7 of a degree gives me the ratio of 400 to 1.
This means that the Sun is 400 times further from the Earth than the Moon is. So, using trigonometry, the Indian mathematicians could explore the solar system without ever having to leave the surface of the Earth.
The ancient Greeks had been the first to explore the sine function, listing precise values for some angles. But they couldn't calculate the sines of every angle. The Indians were to go much further, setting themselves a mammoth task. The search was on to find a way to calculate the sine function of any angle you might be given. The breakthrough in the search for the sine function of every angle would be made here in Kerala in South India. In the 15th century, this part of the country became home to one of the most brilliant schools of mathematicians to have ever worked. Their leader was called Madhava, and he was to make some extraordinary mathematical discoveries.
The key to Madhava's success was the concept of the infinite. Madhava discovered that you could add up infinitely many things with dramatic effects. Previous cultures had been nervous of these infinite sums, but Madhava was happy to play with them. For example, here's how 1 can be made up by adding infinitely many fractions.
I'm heading from 0 to 1 on my boat, but I can split my journey up into infinitely many fractions. So I can get to a half. Then I can sail on a quarter, then an eighth, then a 16th, and so on. The smaller the fractions I move, the nearer to 1 I get. But I'll only get there once I've added up infinitely many fractions.
Now, physically and philosophically, it seems rather a challenge to add up infinitely many things. But that's the power of mathematics, to make sense of the impossible. By producing a language to articulate and manipulate the infinite, you can prove that after infinitely many steps, you'll reach your destination.
Such infinite sums are called infinite series, and Madhava was doing a lot of research into the connections between these series and trigonometry. First, he realised that he could use the same principle of adding up infinitely many fractions to capture one of the most important numbers in mathematics, pi. Pi is the ratio of the circle's circumference to its diameter. It's a number that appears in all sorts of mathematics, but is especially useful for engineers because any measurements involving curves soon require pi. So for centuries, mathematicians searched for a precise value for pi.
It was in 6th century India that the mathematician Aryabhata gave a very accurate approximation for pi, namely 3.1416. He went on to use this to make a measurement of the circumference of the Earth, and he got it as 24,835 miles, which amazingly is only 70 miles away from its true value. But it was in Kerala in the 15th century that Madhava realised he could use infinity to get an exact formula for pi.
By successively adding and subtracting different fractions, Madhava could hone in on an exact formula for pi. First, he moved 4 steps up the number line. That took him way past pi. So next, he took 4/3 of a step, or 1 1/3 steps, back. Now he'd come too far the other way. So he headed forward 4/5 of a step. Each time he alternated between 4 divided by the next odd number. 4/7, 4/9, 4/11, and so on. He zigzagged up and down the number line, getting closer and closer to pi. He discovered that if you went through all the odd numbers, infinitely many of them, you would hit pi exactly.
I was taught at university that this formula for pi was discovered by the 17th century German mathematician Leibniz. But amazingly, it was actually discovered here in Kerala 2 centuries earlier by Madhava. He went on to use the same sort of mathematics to get infinite series expressions for the sine formula in trigonometry. And the wonderful thing is that you can use these formulas now to calculate the sine of any angle to any degree of accuracy.
It seems incredible that the Indians made these discoveries centuries before Western mathematicians. And it says a lot about our attitude in the West to non-Western cultures that we've nearly always claimed their discoveries as our own.
What is clear is the West has been very slow to give due credit to the major breakthroughs made in non-Western mathematics. Madhava wasn't the only mathematician to suffer this way. As the West came into contact more and more with the East during the 18th and 19th centuries, there was a widespread dismissal and denigration of the cultures they were colonising. The natives, it was assumed, couldn't have anything of intellectual worth to offer the West. It's only now, at the beginning of the 21st century, that history is being rewritten.
But Eastern mathematics was to have a major impact in Europe, thanks to the development of one of the major powers of the medieval world. In the 7th century, a new empire began to spread across the Middle East. The teachings of the Prophet Muhammad inspired a vast and powerful Islamic empire, which soon stretched from India in the east to here in Morocco in the west. And at the heart of this empire lay a vibrant intellectual culture. A great library and centre of learning was established in Baghdad. Called the House of Wisdom, its teachings spread throughout the Islamic Empire, reaching schools like this one here in Fez. Subjects studied included astronomy, medicine, chemistry, zoology, and mathematics.
The Muslim scholars collected and translated many ancient texts, effectively saving them for posterity. In fact, without their intervention, we may never have known about the ancient cultures of Egypt, Babylon, Greece and India. But the scholars at the House of Wisdom weren't content simply with translating other people's mathematics. They wanted to create a mathematics of their own, to push the subject forward.
Such intellectual curiosity was actively encouraged in the early centuries of the Islamic Empire. The Quran asserted the importance of knowledge. Learning was nothing less than a requirement of God.
In fact, the needs of Islam demanded mathematical skill. The devout needed to calculate the time of prayer and the direction of Mecca to pray towards. And the prohibition of depicting the human form meant that they had to use much more geometric patterns to cover their buildings. In fact, the Muslim artists discovered all the different sorts of symmetry that you can depict on a two-dimensional wall.
The director of the House of Wisdom in Baghdad was a Persian scholar called Muhammad al-Khwarizmi. Al-Khwarizmi was an exceptional mathematician who was responsible for introducing two key mathematical concepts to the West.
Al-Khwarizmi recognised the incredible potential that the Hindu numerals had to revolutionise mathematics and science. His work explaining the power of these numbers to speed up calculations and do things effectively was so influential that it wasn't long before they were adopted as the numbers of choice amongst the mathematicians of the Islamic world. In fact, these numbers have now become known as the Hindu-Arabic numerals.
These numbers, 1 to 9 and 0, are the ones we use today all over the world. But Al-Khwarizmi was to create a whole new mathematical language. It was called algebra and was named after the title of his book, Al-Jabra wa al-Makbal, or calculation by restoration or reduction. Algebra is the grammar that underlies the way that numbers work. It's a language that explains the patterns that lie behind the behaviour of numbers. It's a bit like a code for running a computer program. The code will work whatever the numbers you feed into the program.
For example, mathematicians might have discovered that if you take a number and square it, that's always one more than if you take the numbers either side and multiply those together. For example, 5 times 5 is 25, which is one more than 4 times 6, 24. 6 times 6 is always one more than 5 times 7, and so on. But how can you be sure that this is going to work whatever numbers you take? To explain the pattern underlying these calculations, let's use the dyeing holes in this tannery.
If we take a square of 25 holes running 5 by 5 and take one row of 5 away and add it to the bottom, we get 6 by 4 with one left over. But however many holes there are on the side of the square, we can always move one row of holes down in a similar way to be left with a rectangle of holes with one left over.
Algebra was a huge breakthrough. Here was a new language to be able to analyse the way that numbers worked. Previously, the Indians and the Chinese had considered very specific problems, but Al-Khwarizmi went from the specific to the general. He developed systematic ways to be able to analyse problems so that the solutions would work whatever the numbers that you took. This language is the one that's used across the mathematical world today.
Al-Khwarizmi's great breakthrough came when he applied algebra to quadratic equations, that is, equations including numbers to the power of 2. The ancient Mesopotamians had devised a cunning method to solve particular quadratic equations. But it was Al-Khwarizmi's abstract language of algebra that could finally express why this method always worked. This was a great conceptual leap, and would ultimately lead to a formula that could be used to solve any quadratic equation, whatever the numbers involved. The next mathematical holy grail was to find a general method that could solve all cubic equations, equations including numbers to the power of 3. It was an 11th century Persian mathematician who took up the challenge of cracking the problem of the cubic.